All right, so here we are, lecture 16b, energy equation intro, and we are, of course, working example problems. And this is going to be the second example problem from this lecture and the final, okay? This one we won't take as long with it. There's one more thing in this problem statement, which is neglect head losses, okay? So basically they're saying there's no energy on this, there's no friction on this one, okay? Another way to say that is it is inviscid, or is to say that it's irrotational. We won't get into why it's called irrotational in this particular problem. Okay, so anyway, so we know a flow rate through this pump system. Okay, it is pumping the water uphill in this case. Okay, so that's the direction of the flow. And basically this flow is starting in a 12-inch pipe, and it is contracting into a 6-inch pipe. There's a manometer connecting the downstream end to the upstream end. Okay, the manometer is filled with mercury, and this thing is pumping oil. Okay, I really love this problem. Okay, now before we dive into this, we're looking for the work of the pump. So one thing we know, if just to kind of give ourselves a little bit of planning about which way we're going to go here, is that the work of the pump is the gamma of the fluid times HP times Q. Okay, Q is already given. The gamma of the fluid, well, we know it's oil with a specific gravity of 0.88, so that's not difficult, is HP. We need HP, which means we are going to need the energy equation. So let's go ahead and grab our tools over here. Okay, oh, well, we won't know what they are. Okay, you have no idea. These are just random words. They're not tools. Okay, anyway, we'll leave the word tools up there because... Anyway, so here's what we got. We got a whole bunch of stuff going on here. Well, it's actually not that much stuff, but there's some thought that needs to be given here. Okay, so what I'm going to do is, the way I like to do this is, because I'm looking for HP, I'm going to use energy as my master equation. Okay, so what I'm going to do that is, before I even write it, I'm going to define a control volume. Okay, now this is key. Where do we want our points to be? Okay, a temptation here, so I want to note that right here, this has the drawing that says that these pipes continue on indefinitely. Okay, so I could make the control volume basically the whole picture, but I don't think that that's going to be a very smart move. Okay, and the reason for that is because the manometer tells us something very specific about the energy at this point right here as it compares to this point right here. Okay, so if I use any other points in this flow as my ins and outs, then I'm not going to be able to use the manometer in the information that it gives. So what I'm going to do here is I'm going to make my control volume look like this. Okay, it's including the pump. I just don't feel like drawing around that. Okay, so here's my control volume. Okay, and I think it technically includes this manometer, but it doesn't really matter because nothing is really happening in the manometer from an energy standpoint. Okay, I guess the entrance and exit of that pipe is creating like a little friction right in here and right in here, but we're not going to deal with that, right? Okay, so once we do that, I'm going to go ahead and call this side right here, I'm going to call that 1, okay, because I don't feel like writing the ins and the outs, but really that's the in, and this is the out, okay? I just prefer to write the 2 and the 1, okay? And you'll probably prefer that as well. Maybe you won't. You can write ins and outs. Okay, so what we need to do is I'm going to use the energy equation as my master, and what I'm going to do if I use the energy as my equation, as my master, is all the things that are going to go into the master are going to be my asides. Okay, and I'm going to put them over here so they're out of the way. Okay, so the master equation. Yes, master. Okay, plus alpha v1 squared on 2g plus hp equals p2 on... Note in the future, I'm sure that I will just have this pop up, but since at this point you are just learning this equation, I'm going to take a little time with it. Okay, HL, or H turbine plus HL. Okay, the first thing I'm going to do is I'm very quickly going to knock out the terms that don't exist. Okay, we're neglecting head losses. That means there's no head loss. Okay, there is no turbine in this problem. Okay, there is a pressure at 1. There is a pressure at 2. Okay, there is a Z at 1. There is a Z at 2. There's velocities at 1 and 2. So all these, and there's a pump. So all these other terms exist. All right, but we can't really get at any of these. Okay, and that's problematic. So what I want to do here is I want to start thinking about my tools and which ones I can use to get at things. Okay, so what I'm going to do, oh wait, let's see, can we rule out any of these tools? Well, we can rule out momentum because we're not dealing with a force on a moving fluid. Okay, nothing in here says anything about forces. Okay, we're going to need the manometer. And how are we going to use the manometer? Or what are we going to use the manometer for? Well, the manometer is for measuring pressures. Okay, so that's going to help us with P1 and P2. What are we going to use continuity for? We usually use continuity to get at velocities. Okay, what are we going to use the geometry for? Usually use the geometries to get at Z. Okay, so let's start with the geometry. Okay, geometry. Geometry, brah. Okay, some of you guys are probably from Metry, brah. Some of you guys have no idea what that is. Anyway, oh, something happened over here. I wonder if my hand must have hit that. Okay, so the geometry. So I want this to be my datum right here, where 1 is, right, ideally. So I can make this my datum. Okay, and then what is this? Okay, so there's a few different ways to kind of get at that. So I can make Z1 equal the datum. And then make Z2 equal to, I don't know, let's just call it H. Why not? Okay. Now, a lot of you are resistant to do that. You can call things things. That's what algebra is all about. Okay, so I'm just going to call that lowercase h. Okay, so now we're done with our elevations. We are ready to roll. Okay. Okay, now let's do continuity. Continuity. Okay. And so, do I know Q? I do know Q. Sweet. Okay, what else do I know? Well, I know these cross-sectional, these diameters. Okay, so I can say right off the bat, by virtue of the fact that this pipe has twice the diameter of this pipe, that this pipe, okay, pipe 1, has 4 times the cross-sectional area, which means pipe 2 is going to have 4 times the velocity. So I can say that V2 equals 4 times V1. Okay, that's pretty cool. And then I can use my continuity to get out exactly what those values are. But using this, I'm only going to solve for one of them and then know the others. Okay, so I'll go ahead and solve for V1 equals, let's see, V1, Q equals V1, you know, when you get ahead of yourself, V1, A1. Okay, and let's like move that. Oh, no. Anyway, it's just not going to be where I want it to be. Let's just move it where I want it to be. Okay, Q equals V1, A1. So V1, so Q is 5 CFS, that's cubic feet per second, not centifeet per second, equals V1, which is what we're looking for, and A1, which is pi times 1 foot squared on 4. Okay, so V1 equals some number. It looks like it's 6.366 feet per second. Okay, which means that V2, which is 4 times that fast, is 25.465 feet per second. Okay, so now we're getting somewhere. Sweet. Okay, so if I go over to this equation, okay, let's see. From the geometry, I've got my Z's. Okay, from this, I've got my V's. Okay, note that the velocities have to be the same because it's in equals out, right? So this is one flow coming in, one flow leaving. Okay, and then we need to get those pressures. Okay, so how do we get the pressures? Okay, we said we're going to use the manometer. That makes perfect sense to me. I guess for this aside, I'm gonna do it up top just so we can see the manometer while working on it. Okay, manometer. Manometer. Okay, anyway, I hope y'all are Sesame Street or Muppet fans. All right, so we're going to start at 1. Okay, again, remember, this is how we know that we are, you know, I told you needed to know the manometers. Okay, so we're going to start at 1, and I'm going to go down some bit. Well, I'm going to go over just a smidge. And we don't care about going to the left or right. We only care about going down. How far down did I go? Okay, I want you to remember something you did with this H. You made up a letter. Let's make up a letter. What's a good letter for that? Let's use capital H. Okay, so capital H is going to go from here to there. Okay, so I went down some capital H. Okay, so when we go down, the pressure increases. So that's going to be gamma of the oil, because we're moving through oil, times capital H. Okay, at this point, I hit the mercury. Right, I'm going to go down through the mercury, over, back up to right here. Okay, notice we're right at the same point. So, oh, you know what? We went too far, didn't we? We went too far. You can't do that, right? We can only go back to this point right here. Okay, so I went down in the mercury. So we're going to say, let's see here, we need black. Plus, okay, gamma of the mercury times that 3 feet. Okay, I hate using 3 feet. Anyway, whatever. We'll just put in the 3 feet. I like using all symbols. But anyway, so we went down 3 feet. All right, so now we're going to now we're going to come back up. So we're going to go minus gamma of the oil minus the gamma of the oil times that 3 feet. Oh, I hate that 3 feet. Showing up twice. All right, but then we're going to keep coming up. And we're going to come up, let's see here. We're going to come up here, big H, and then lowercase h. Whew. Right, so we didn't just come up 3 feet. We came up 3 feet plus lowercase h, or big H, plus lowercase h. And that got us to P2. All right, so that's the manometer equation. Now you're like, man, I didn't want to make up those symbols because now I got all these symbols everywhere. Okay, whenever you have to make up symbols, either I didn't give you something, or, well, it's true I didn't give you something, obviously, unless you just read it wrong, or a lot of times it's going to cancel out. Okay, so let's rearrange this. I'm going to bring P1 over here. So I'm going to have P2 minus P1. Okay, then I'm going to divide both sides by gamma oil. Okay, equals, and I'm going to be left with, let's see here, H plus gamma Hg on gamma oil times 3 feet minus, let's see here, the gamma oil has been canceled, excuse me, minus 3 feet plus H. Okay, now what do you see is happening here? Well, look, one of those has gone away, right? This capital H is going to cancel with that negative H right there. When I do those gammas, they're going to do the nice thing and run away so gamma Hg is going to be SHg over the gamma times the gamma of water. S oil is going to be S oil times the gamma of water. So the gamma of water is going to cancel times 3 feet minus 3 feet plus H equals P2 minus P1 over gamma oil. Right? And I should have just now, instead of SHG over S oil, I should have put in 13.6. 13.6 over the the S of oil, which is 0.88. 0.88. Okay? So I'll write this finally as P2 minus P1 over the gamma oil equals 43.36 feet minus H. Okay? Whew. All right. So now we've got something about P2 and P1. And basically that thing, what it does is it allows us to not write down either one of them. Okay? So I'm going to rewrite this equation now, noting that this whole thing is an oil, so this needs to be a gamma oil because that's the fluid we're dealing with. And I can just start plugging these suckers in, right? So I'm not going to show those equations. I'm going to assume that you took some notes here. So P2 minus P1, son of a jerk, okay, over gamma oil, okay, plus Z2 equals HP, gamma V1 squared on 2G, Did we forget anything? Plus gamma V2 squared onto G. Okay, so we've got both pressures accounted for. Oh, we need a Z1. Z1. Okay, which turns out to be 0. So that's everything. And we're going to start plugging numbers in. Now we need to deal with these alphas real quick. So let's go ahead and deal with the alphas before we get over here. Okay, so now let's get a Reynolds number. Let's go down here. This should really come right after we get our continuity, right? Because we know that we're going to need this. Okay, so alpha 1 and alpha 2. Okay, so the Reynolds number is VD over nu. Reynolds number is VD on nu. Okay, so the velocity is 6 feet per second, and this one is 25 feet per second. Okay, the diameter 1 is 1 foot. Okay, the diameter 2 is 0.5 feet. Okay, and the viscosity is more or less 10 to the minus 5 feet squared per second. It is 10 to the minus 5 feet squared per second. Equals. Okay, plugging and chugging, I end up with 6 times 10 to the 5th and 1.3 times 10 to the 6th. You will note, if you plug this into your calculator, if you're following along, that 25 times a half is 12 and a half. So 12 and a half divided by 10 to the minus 5, that's 12 and a half times 10 to the 5th, which can be converted into 1.25 times 10 to the 6th. And I could have kept it like that, but this is more than enough significant digits. Okay, this is more than enough significant digits to tell whether or not this is turbulent or not, right? So we're basically testing, how does it compare to 4,000? Okay, so the Reynolds number for like the transition in a pipe, I don't know what you want to call that, transition in a pipe, is about 4,000. Okay, we're way above that. Okay, this is 4 times 10 to the minus 10 to the 3rd, right? We're at 10 to the 5th, 10 to the 6th. We're golden, right? We're golden. So this is turbulent. Okay, this one's turbulent, this one's turbulent. So alpha equals 1. Okay, it approximately equals 1. Alpha equals approximately 1.0. Okay, so that's what we're going to use. Okay, so yeah, so that's all you need to do. Some of you will note that if you look up this number for 50 degrees, you will actually get 1.41 times 10 to the negative 5, 1.41 times 10 to the negative 5. You're more than welcome to use that number. Again, notice that 1.41 is not going to make a what's a clean way to say not very much. It's not going to make any difference. Okay, so so don't worry about that. Okay, so alpha is 1. Okay, so now we're ready to solve this sucker. And the nice thing about alpha being 1 is we can go over here and I can just go, okay, so this alpha kind of goes away. This alpha goes away because you multiply anything by 1, you get itself. Okay, so now we are ready to roll. Okay, we should also know that these velocities, these are average velocities. Okay, so let's go ahead and solve this. So Z1, 0. V1 squared on 2G. What's V1? 6.3666 feet per second squared on 2G. 2 times 9. Oh, no, don't do that. All right, careful. 32.2 feet per second squared plus HP. That's what we're looking for. HP equals P2 minus P1 over gamma oil. 43.36 feet minus H. Okay, plus Z2 is lowercase h plus V2 squared, which is 25.465 feet per second squared, all over 2 times 32.2 feet per second squared. All right. Now look at that. Isn't that wonderful? They all came out to play lovely, and they canceled. Da-da-da-da. You got to be all happy when that happens, right? Because it means something. It's very good. It's very good, right? We should be very happy at moments like this. So we are left with 0.629 feet plus HP equals 43.36 feet plus 10.07 feet. Okay, so I'm going to solve for HP. And before we move on, I want to stop and talk about this real quick. 52.80 feet, or 52.8. I don't want that 0 in there because we like to report 3 sig figs and not all those extra ones, okay? All right, so question for you. Okay, I want you to think about what all is going on here. I've got a certain amount of energy coming in. Technically, it really is only this, 629, right? It's very little velocity is coming in, and I've got this pump hooked up. And what this pump is doing, it is basically pressurizing the fluid a lot, 43.36, and it's giving it more velocity head. Okay, because the velocity head is so much, because the pressure that is on the upstream side of the pump is so high, then this thing has to have a lot of head. Okay, 52 feet of head. Okay, so that's what this thing is doing. All right. Okay, cool. So let's go ahead and solve this. I want the power of the pump, not to be confused with the power of the people, right? Oh, vote day is coming up. You guys should go vote. That's all I'm saying. Okay, vote for whom you think is correct. Okay. All right, so we've got this thing right here. I will note that this gamma, that's the gamma of the oil. Why the oil? Because that's what we're pumping. Okay, so if you're wondering, it should be the one that we're pumping. Okay, so we're going to go W dot pump equals the gamma of the oil, which is 0.88, times the gamma of the water, which is, I almost wrote 9810, right? You got to be careful with that. 62.4 PCF. Okay, HP. What is HP? That's 52.8 feet. And what's the Q? I think this was given as 5 CFS. Okay, this is an annoying set of units, right? But we got to learn how to deal with it. Okay, so let's see what it does here. Let's just see what it does. Okay, so if we multiply all this into our calculator, we get the grand total of 14497. Okay, now what are the units on that? Okay, so if ever you're stuck and you're like, I don't remember what the units are power. Don't worry about it. You got it right in front of you. Right, we've got a pound per cubic foot. We've got a cubic foot right here. So the cubic feet go away. So I'm left with pounds. I'm left with 1/seconds over here. And I've got a foot coming from right here. Oh, cool. So in other words, I've got foot-pounds per second. Okay, this is a torque or a work per time. Okay, foot-pounds per second. Now, unfortunately, that's a fairly large number. So, I mean, I guess you could do this as like W dot pump equals, we can make that kips, so we can make it 14.5 kilopounds feet. They must do something like that per second. Could do that. What's more common here in this stupid English system where nothing makes any sense is to divide this number right here by 550, and you'll get horsepowers. Okay, now this is a very problematic thing to do. Every now and then a problem will ask for this, and I'm going to ask you why in a second. Okay, 26.4 horsepowers. Okay, why is that a problem? Okay, so we just divide this number by 550 because 550 horsepowers equals, 1 horsepower equals 550 foot-pounds per second. Okay, so this is 500 foot-pounds per second. Okay, so what is the problem with this? Okay, now if you're using, if you're typing, it doesn't matter, but here's the problem. This thing right here, horsepower, looks an awful lot like the head of a pump. Okay, in this case, that's like a subscript, and here it is not. Okay, so I ask you to be very, very, very careful. If a problem gives you horsepowers or horses power, okay, just remember that that is not the same thing as the head of the pump. Okay, so just be very careful with that. Okay, so that's all there is for this problem. This is one of my favorites because it uses so many of the tools. You will almost certainly see something like this on a test. There is a test yet, but this won't be on the second test. But I love this problem. I absolutely love this problem, and so do whoever writes these problems for textbooks and things like that. Okay, I could easily give you this exact same problem on a test, and just flip the flow, make the flow go that way. Totally different problem. Well, it's not a totally different problem. It's a lot of the same stuff. But, I could give you a head loss in there if I wanted to. The same problem. Okay. There's so many different ways I could draw this. That would be quote unquote tricky. I wouldn't draw this in a tricky way. One of my favorite ones, I'll just mention this. This is one that ended up being tricky that I didn't mean to be tricky. Was on a test, one of the old tests. I had a manometer that looked like this. I can't remember exactly how it worked, but it was something like this. Yeah, I don't know. Okay, we had a fluid here. It kind of went over here, and then it went to like right there. Okay, and then what they told you was that from here to here was like, I don't know, let's say they said that was 2 feet, and so this was like 20 degrees. Okay, for reasons that I cannot understand, so in this manometer equation, let's suppose this is connecting up to like a tube, and the fluid is flowing past. Okay, and somehow I could see how this would confuse people. Okay, so we've got a fluid flowing past, and what people did is they started to use this 20 degrees C. Now, I don't know why they would do that though, right? Because here's the thing. When you do your problem, you start at P1, you start at point 1, you go into point 2, okay, so you go down, so it's P1 plus gamma of whatever this fluid is, okay, times whatever that distance is. We'll call that H, let's say. We'll call that H. Okay, now we're going to go down. We're now in the black fluid, so gamma of the black fluid. And we go down to here. We've gone down 2 feet. Okay, what does that 20 degrees have to do with anything? Oh, yeah, it's got nothing to do with anything. Right? And then when we go back up, now we're going to go back up that 2 feet, and then we're going to go up the H. So we're going to go minus gamma of the fluid times the 2 feet plus that H. That's how far up we went. Equals P2. Okay, so just be aware. I mean, the way I would do this now that we've got energy problems and things like that is I would put a pump, or maybe I'd put a turbine right here. Okay, if I wanted to. I could do that. I could put a pump right here. Okay, I could put energy loss along these walls. Okay, we're getting to some point where you guys can handle almost everything. Okay, obviously if I were doing this sort of thing, and maybe not obviously, but I would do like this, P2 minus P1. I would divide by the gamma of the F. Okay, and that would give me H plus gamma B on gamma F times 2 feet minus 2 feet plus H. I don't know why that has an H bar or H prime, right? I'm just going to complete this. Obviously the lecture's over. Just kind of getting excited, because, we got to get excited sometimes, guys. I'm just saying, get excited, be excited. Okay, notice those H's go away as they are wont to do. Okay, this becomes SB over SF times 2 feet minus 2 feet equals P2 minus P1 over the gamma of the fluid, and that is ready to plug into your manometer or energy equation. Okay, so be able to do this. This should be quick. Okay, usually on a big problem like this, that little bit right there is worth like 2, maybe 4 points, right out of 10. Okay, but it should take you, it should be like a 30-second operation. Well, maybe not 30 seconds. Nobody's that fast. Maybe somebody is. I'm not. But anyway, it should be like a minute or two. It shouldn't take you too long. There shouldn't be too much thought. Maybe a little bit of time figuring out the algebra, being careful. But lining all this up, doing this first line, should be very fast. Okay, so make sure you can do it. If not, I'm here. Come to office hours, guys. I'm here to help. All right, anyway, take care of yourselves. Hope to see y'all soon. And goodbye.